Hello and welcome. I'm Bill Wake. We're here working on the basic interpreter BASI, and we've gotten to the point where we've got functions, both user-defined and predefined, and we want to type check our predefined functions. Some of them take strings and or numbers as arguments and return strings or numbers, so we want to get that all straightened out. All right. And we left off with a failing test. Okay, so if you try and print square root of a string, we expect a type mismatch error. And we're getting nothing, no errors. Okay, so here's the place where we do function call, and we've got the variable. Oh, this is user defined. Let's go to predefined. Okay. We've got the name and the type of the function. Okay, and we skip over that. Got a left parenthesis, expression, right parenthesis. So there's the argument. In the future, we'll add commas and multiple arguments, but right now we don't have that. So we need to check the type and make sure that the expression has the type that our type requires. Okay, and I think I'm just going to do a type check, and let's pass in let's pass in the type and the expression. Okay, and the idea is this method will examine the type and determine if the expression is compatible with the argument type. So this is a function type. It takes arguments of a certain type and returns a certain type, and we'll figure that out. All right, so type check. Let's just define it here. All right, and the type, this is a throws. Okay, the type, we expect it to be a function type, because it's coming in off this predefined function. So let's make sure the type is a function type. Case we want to say dot function of let operands and then nothing. We don't care about the return type for this statement. Equals type else, and I'm going to throw an internal error. I don't know if we actually have one. Yeah, let's make one up. It's kind of a can't happen case. And I guess we could assume it takes a string that says function has non-function type. Okay. And so we'll need this. And that's kind of early on. Case internal error. Okay, those two are both kind of like that. Now, do I have a navigate? I got so used to like command left arrow, command option left arrow. Nope. Command control. No. Okay. I don't know if there's a way to get back where I was, but down here is probably a good choice. All right. Internal error has no associated values. Oh, yeah. We'll just give that a string. Okay. So the function type, let's go look at that. It takes an array of types, which is the argument types, and it takes a single type, which is the return type. Okay. And you know what? I'm gonna go ahead and I'm gonna pass that in as a list, just to kind of make things a little easier. Expers. Okay. Now, if if the operands is not the same number as the expressions, then we've called it with the wrong number of arguments. Okay, so if operands.count not equal expers.count, well, let's save that. I guess our test isn't there yet, but I'll just add a note here. Okay. So the check we're doing is basically the types. So, I want to rip through both things. Well, let's assume they're the same. Can I just do operands for each? Okay, so I've got every operand. Let's operands dot enumerated. Yeah, that gives us the integer and the I'll say index, I guess. I don't know. All right. So basically we're ripping through the list of operands, and we want to make sure that I guess we want to make sure that each one I guess if operand is a type, I guess this is parameter type, probably more accurate. Type mismatch. Okay, so we run through each operand. Run through each operand, get the index and the parameter type, and then check the parameter type matching the type of this. And if it doesn't, we throw an exception. So I believe that should pass. Build failed. Okay. looks like a parser must conform to equatable. Okay. Where's parser? There we go. I guess I got it for free when they were simple, and now I've got the string in there. I've got to say equatable. Don't know why it doesn't complain there. All right, let's try again. Now, the errors and stuff, we've got some room for improvement. All right, but that passes. Let's check the argument count as well. I think we've got a function or two that number of arguments. Okay, so these functions, the simple ones do, but the ASCII ones we can do left dollar. Actually, that'd be a good test. I don't know if we'll parse that correctly. Let's see. So number of arguments. So print left dollar. Let's just put the string and leave off the I. Okay. And this should be an argument count mismatch. And we'll add that here. Where's missing match? Okay. Argument count mismatch. Good. All right. Let's see how it does. Okay. So one problem, maybe it doesn't look for left dollar. I think extra characters at EOL. Yeah. Let's check our lexer. So we don't have reserved words with dollar signs in them until we added these functions, and I think maybe maybe we're not prepared to look for dollar signs. Okay, keywords and names. Yeah. Okay. I guess what we're seeing, we want to allow for the possibility that there's a dollar sign after all the letters. Okay, so I don't know. This is probably not the right place to fix this. Actually, there's no probably about it. It's not the right place to fix this. Let's add a lexer test. Test reserve word. Let's go ahead and add. Do we have any? Okay. Let's. Okay, so test function name with dollar sign. And I think we don't need the whole thing. We'll just make sure the character after it's there. That should be left dollar. And the type is SN to S. SN to S. Oops. Okay. So functions with dollar signs should be accepted. This one will not. We'll run that test. Okay, and it's, yeah, L, a variable L. Right, so left, since it doesn't match the left dollar, it doesn't match any reserved word, so it just says, oh, this must be a variable L, followed by a variable E, followed by a variable F, you know, eventually down, followed by a weird dollar sign. So I think, let's see, do we have one that just accepts one character? So this one, right, so it runs through reserved words, trying to find one that matches, wait, what's token? Oh, token's the result, yeah. So value starts with word. Yeah, so we just need to see if there's anything that lets us grab one character. I don't think we did something like that. Normally we just check it. Yeah. Okay, so we'll just check it. See, here we allow for that. So we've skipped any A's through Z's. If program subindex is a dollar sign, then let's add that there. Is that going to work? Okay, so we basically peek ahead. Yeah, I guess we're grabbing any string of letters, and that gives us sort of a head to look at. So in 275 we pick up the starting index and then peek forward through all the letters and dollar signs and optional trailing dollar sign anyway, and then we start the index back. I'm not sure this does anything. Index equals starting index. Okay. Value. Oh, value is, okay, repeat any actually grabs, returns a substring. Okay. We'll need to deal with that then. Do I need? Yeah, repeat any only accepts A through Z. Who uses this? Okay, digits and letters. Okay. We really need to append the dollar sign here. Let's try that. Bar value equals repeat any. If this, it's not so much the index that matters, it's that value plus equals dollar sign. Okay, so we get all these strings. I don't know if it'll let me do this because it's substring stuff. Let's try it. It may complain. Okay. Good. All right. And now let's try this predefined. Which should fail because we don't actually check those yet. Parser. Yeah. Okay. So we access the first one and match it. It's okay, but then we try and grab the second one and we got a problem. So this is here. If operands.count not equal to expers.count, then we're going to throw parse error. Oh, come on. Be so picky. Parse error.argument count mismatch. Okay. Good. Okay. Let's check that in. All right. So we added Lexer support for predefined function names ending in $, and we added type checking for predefined functions. Okay. All right. Now I think there's. I sort of argued yesterday, like, oh, we got to check this the user-defined ones at runtime because we don't know what the definition is going to be. But that's actually not true. We know the type. Oh, and there's something else going on. Bubbles around here. These functions like left $, that they return a string, and I don't know if our parser understands that that's a string. Okay, so the function, yeah, something's just a little weird. Yeah, so this can't be right. Predefined something float. It's the return type. I can understand if it's the return type of an expression. So if you say function of int number goes to number, the type of the function should be that number that it goes to. If you said a function goes to a string, that type should be string. Okay, so I think we're missing. I don't know. We're definitely something's up because this is too naive. This one's okay because these functions always are float to float. But predefined, let's get to the definition. String expression. String is the name. See, I feel like the type has to bubble along with it, and we don't have that. Okay, so type check predefined functions. I guess let's say function calls. That's what we've done. But I think we also want to type check function results. Okay, and I also think we want to. I think we're going to need to carry the type along. So here the operators, they assume. Again, they make an assumption that it's float, which is Well, actually that's okay in a sense because the only unary operators we have are not, which works on numbers in BASIC, and minus. So it has to return a float. Operator two, um, well, plus, minus, divide, all those things, they do work on numbers. There are basics that have plus as a string operator, and then that would not be right. But I think that part's okay for now. Now you can say we don't have any operations that work on strings, so all you can do is call a function. You can have a string constant, or you can call a function that returns a string. And so I think that's this case that needs a type in it, and then needs to say the type is that. And this one probably should too, just to be parallel. I mean, like whatever it says the type is, at least the result type. It may be a little work to get to it, but it should do it. Variables, we do return the type. So if you have $, which is a string variable, it knows that it's a string variable and it returns that type. That's good. And the string constant. So you got 2 ways, but not 3. Okay. Let's see. What else do we have? Missing predefined function. I don't know what that is. Remaining predefined numeric functions. Predefined string functions. Well, okay. I want something easy. And maybe I want to do some of these other things. Okay. Move static definitions from lexer to type. Let's deal with that. All right. So the static definitions we're talking about, we have all these N to S whatevers. They're sort of predefined, very common extension type. Okay. So they're predefined common function types, number to number, number to string, and so on. All right. And we took them out here. Somebody should be complaining. Yeah, all these type S to N, they need, I wonder if I can declare these more like this. I think I might like them as free floating kind of things. I'm okay with that, I think. Let's do a build again. Oh, okay. All right. I think maybe we're okay. Yeah. All right. And then the lexer is going to complain. These now need type dot. And this is a finite list. I probably could have just done a string substitution. All right. And let's run all tests. in our to-do, we did this one. And now we've done that one. Let me do this one. Okay. The deal is we've got this function require. It's kind of a helper for the parser. I don't know if I put it up top here. Yeah. So we got something to give you the next token, and we got something that says, I expect this token. If I don't see it, it's an error. But I think if we look at the usages of require, we'll find that every single one is followed by a token. It doesn't implicitly mean that we should couple those, but I think we should. I think we're saying it's required and I'll eat it. Okay. And so let's just go to each of these. Require followed by next token, require next token. Okay. So I think we can go to all the call sites and remove that. All is, whatever that is, 10 cases or so. I could do it incrementally. I should say that. I could define a require, like probably rename this to require old, define a new require that does the next token thing, and then one at a time I could replace the calls from the old one to the new one, and when they were all gone, delete the old one. I think instead, because it's a finite set in one file and I've got them all sitting here, I'm just gonna do it manually. Okay, so I'm taking out the next tokens after any require. And let's say I haven't done these last 4. Let's run the test, make sure something blows up. Okay, right. Good. Where's the fines? Require. And require. Okay, now this test should pass. Dum-dum. What test are we in? Test call user defined function. We're not very far in, are we? Okay. Call user defined function interpreter. Okay, 25 print function I3, implicit 9999, def f and I of x equals x. Okay, let's go check our parser. So this blew up. Okay. Okay, it blew up in here where we're trying to look up the function until our error function not found. Okay, so let's see what we got. I. So that appears like our def didn't do it. That seems right. Okay, parameter. Okay. So our parser, let's look where we define these functions. Okay, use define function. That's the call. Require left paren, expression right paren. That seemed okay. The problem was the definition. It's predefined. I think it's called define. Require function. Whoops. Okay. I think I just missed one. Let's hope that's all it is. Okay. So we made require also consume the required token. All right. Let's take that. I guess that never made it to the screen. All right, what else we got? Expression parser, error handling, and interpreter. That's a bigger job. Okay, I don't know why I don't want to just finish these. Let me do, we're just going to take a couple minutes before the break. So let me do another interpreter thing. And I don't think I'm going to test every single one of these. You may think I'm being stupid. Do I think I'm being stupid? I don't know. But okay, here's the functions. Yeah, so these are the Swift functions in here that correspond to the predefined names. And a lot of these are kind of straightforward. Do I want to worry about that? Sorry, like sine, cosine, tangent, atan. I mean, those are all just clearly what they are. Sine, cosine, oops, sine, cosine, tan, atan. Okay. Maybe we'll do one mega function somewhere. What else do they call it? Atan? Okay. And I think I can put this comma here so next time it's all right. Yeah, so I guess I probably want these alphabetized. There's just so many if you don't. It'll be hard to keep them straight. Okay. Arctan, cos, lens, sine, square root, and tangent. Okay. And then let's add absolute as well. Dot function of into n of abs. Okay. And shouldn't break anything. Okay. I just don't want to have to do all 50 of them at once. Okay. Let's see. Type check function results. That's a good thing to do. Yeah, we need to do that. And same thing, the user defined thing, I need to straighten that out too. This has a type, and we should at least define an implicit type on these as well. Now there, the type comes from the name. Let's find this. Okay, predefined, let name, let token. User defined, function equals token. Yeah, I guess we don't, it's implicit, but it should be there somewhere. Yeah. All right. Let's take a break, like 3 minutes, grab a drink, whatever, and we'll come back and work on function results and predefined functions. I don't know. Like, why don't I just want to finish one of these things? I think we will. There's some work to do to make that happen, but we'll get it. All right. And I'll see you in a few minutes. Hi, welcome back. All right. Returned values of functions. Let's see what we got. All right, so we have the type of the function coming in for predefined. Let's get down there. Whoops. Back to parser. That's the one we want. Predefined function call. All right. All right. So the predefined, the actual call returns the name of the function and the expression. And I think the issue is when you ask value here. Is that who had type? Where was the type? I guess expression, right? Wrong one. Yeah, expression. If you ask a predefined call what its type is, it tells you I'm a float. Okay. And that's wrong. Because we have string predefined functions now. We don't have any defined yet that actually produce the results, but still they should be looking up their type. Okay, and I think that may mean predefined should probably tell us the type. Okay, because we can't get it. Predefined had name and expression, right? So it's the function name and the expression it's being called on, but we need the type as well. Okay, so predefined, where was that? Predefined Is that on parse? Yeah. Predefined's up here. All right. So I'm saying this thing should take a type too. And that should break some things that say, I don't have a type. But I think the type exists and we can get it in there. Somebody has to be complaining. Okay. It seems like more things should complain because whoever creates one is going to have to complain, right? Tuple. All right. Let's put nothing in there for now. And nothing in there for now. Oh, I guess we'll put something wrong. Dot. Float. Okay, and I am changing that name. Something's screwy. Let's build again. Tests? No. Okay. This name, I've called it number everywhere else. Float is kind of the implementation type. Let's rename this to number. Okay. All right. So now everything should be the same. I knew a test would have it. Okay. Number. Number 4. Well, its type should be number. Okay. Let's see if that passes. It should, because we just hard-coded a number in there. Okay. But this, yeah, let's do a string one. Okay, so if you print okay. Let's see, let's find one that takes a $sign. CHR dollar. Okay, so if I print CHR dollar of 4, this type I don't think that's the test I want to do right now. And this type should be the type of the, what should it be the type? It's a call, so let's give the type or the result. Yes, okay, and we're saying that should be string. I think that's okay. Print CHR dollar 4 should be 25 print, and it should be the predefined function CHR dollar, the number 4, and returning a string, and that should fail. Okay, and the type's going to be number. Expected number is not equal to string. Okay, so we need to go to our parser and the function calls, which was the last one, right? User defined function call. Okay. We returned user defined. Wait a minute. We want predefined. Predefined function call. Okay, so we just hard-coded number here, but really it should be the return type. Okay, which is this type. I swear there's a way to assign this. Maybe I'm mixing up like Go or something, but I want to get those fields out of that type. Man, I got to do this guard thing. Okay, this type is the functions type. This type is the return value of the function call. And the function knows that. Okay, so let's do it. Guard. Well, how about if case dot function let okay, let me go in here, type check. We did the same thing down here. Now we want the return type. Okay, let's do it and then we'll straighten it out. Let return type equals type else. Oh no, if case and this is, well, return type equals type. Okay. Otherwise, we're going to do result type equals return type. Okay, result type defaults to number. If this type is a function with a return type, then we're going to take the return type and use it here. Okay, where's that failing test? Okay. Now, can I make this better? Parser. So, yeah, something's still goofy to me. Okay, so let's do this earlier. Okay, so we skipped the token. That was the function call. Okay, let's look at this. Let's get operand types. Is that what I need down there? Yeah, so I want to get rid of this internal error. So let operand types, the type check, let's pass in operand types. And okay. Well, I call them operands. Okay, I think that takes care of that. Okay. If the count doesn't match, that's an error. If the types don't match, that's an error. Okay. But we don't really care about this one. So instead of doing that, I'm, oh, now how do we want to do this? I'm moving the error up, I guess, is what I'm doing. Oh. Case function let operands, types, and result type. Okay, so if the function if the type is dot function from operands to result type, if it's not that, then we have an internal error of some sort. Okay, now we've got the result type. This goes away. Okay, and we use result type down here. Okay, since this result type really must exist if the function is properly declared with, you know, a functional return type, then the throw will never happen. But the result type is what counts here. Okay, now that should still all work. I don't think I pushed it before, so let's hope it does. Okay, so we make predefined functions return their result type. This is calls, really. Okay. And then there's still something wrong. I mean, oh, what's going on here? Why does nobody care that this is wrong? Let's just check parse.type. I think we have parse tests. Do we? Parse, well, it's under parser tests. Okay. Do we have any calls to type in here? Not really. Who's using that? Parse. See, what it feels like to me is somebody's not telling, like, this is not telling the truth about the predefined, and yet nobody's bothered by that. That bothers me. Okay. Expression tests. Number.type is number. Okay. Variable has type. Operators all have type. Yeah, these are more like parse tests. But okay, let's put in a test for the function call. Okay, so let call equal. Oh, I guess these are expressions, aren't they? But they are looking at type, so let's do that. It's predefined, and the name is CHR $, and the expression is an integer dot number 3, and the type is the return type is string, And this call type should be string. Test. Really? Well, this is type. I guess if we knew what predefined was, the rest of these would happen. It's an expression. Why are you not happy? Expression.predefined. So I don't really have to say type here. Whoops. Okay. Good. All right, and this will fail, we believe. Okay. Now, how would we... Yeah, I'm still bothered that nobody's looking at it. Who cares, right? Who's the thing that cares? I guess if we did an assignment, A equals CHR $3, right? That should be a problem. Okay, so before we fix it, let's do a parser test. So I want to check error. Predefined function. Can't assign predefined string function call to numeric variable. Okay, so if I do A equals CHR $17. Okay, I should get a type mismatch. Yeah, because this returns a string and this is only a variable. And let's see what happens. I believe it's going to fail. Oh no. No, yeah, how, wait a minute. Did that run? I think it should fail. I really do. There it is. Okay, because I think what happens is right now we just lie and say that this thing is numeric type in the type here, and the assignment says, oh, numeric equals numeric. It's a fine. All right. So this, I want to fix both these with the same thing. So parse the user-defined type. Down here, we should do let the type, or let type, and return type. I think we can say type here. Reserved word. Okay. And so all these should pass. Okay, I feel better. Yeah, so I was not enforcing the result types before. Now I think we are. Now user-defined types, they always are numbers, so maybe we don't need the type there. All right, let's see. So make predefined functions declare their result type in the function call, which is checked, properly checked. Okay. Right. This is good. And I think this is accurate. Every expression tells me the type. If I have string expressions, they bubble up as strings. You can't operate on them at this time. All right. Now, what else do we have? Type check function results. Okay. Now let's look at the case of the predefined function calls. We're not the user-defined ones. We really should enforce these as well. Okay, so if I call f and I of string, do I have a case like that? Well, let's look for fn. F and I of 3, that's fine. F and I must have numeric result. Okay. Yeah, so I don't really check this case. That's more syntax. Okay, yeah. Well, this is more of a check error. Check error. And if I do print function I of a string, the def call must take a numeric argument. So function I of a string is not legal because it's supposed to be of number to number. And we should get a type mismatch. I don't think we will. Should be empty. Yeah. Okay. And I think it's the same. This type check is perfectly fine for it. Okay. Type check. Well, operand types is just number, and expr is the only expression because we only allow one argument user-defined functions. All right, but its return type, sorry, it's the expression type, the argument type must be number. All right. Like I said, I don't know, this resistance, that take 3 minutes to fix. Okay, so enforce that function calls only take numeric arguments. All right, type check function results. That we've done. Handle the case of a missing predefined function, remaining predefined functions, remaining predefined string functions. Again, I don't know. I just I want to do other things. I just, for my own whatever it is, doing the same stuff, functions, just like the missing predefined function. Well, okay, that's, I guess, an interpreter thing. I think we said something about this the other day. Call predefined function. Yeah, so I think what happens if we don't find it here, we just blow up. That's, I mean, we get an exception at runtime. That's, I don't know. Theoretically, it doesn't happen. The reason it's happening is because we just don't have these things defined. All right, so let's let's just define them. I don't know, the string ones I'm not quite so ready to do, but the numeric ones, there's really no reason not to. Okay, absolute, that's easy. Int, largest integer less than x. It's like a truncate, maybe. I don't know what we call it in Swift. Okay, but int of x. Okay, the int function. And let's go find, well, just do this. Whoops. Swift truncate float. Oops. I probably just say int and it does it, right? Casting float to int. Oh, really? Yeah, that's what I thought. Convert to int will lose precision rounding down. Okay, that truncates. Yeah, that's kind of what we want. Okay. So let's see. Int, the function is, well, it's a closure. We're going to take float of int of $0. Okay, so we take the float, convert it to an int, which truncates, and then convert it back to a float, which puts it back in the right type domain. Okay. Random of x. Okay. This one is funny because the original random, section 3.3, I believe. Functions and subroutines. Okay. Int rounds down. Random produces a number between 0 and 1. It requires an argument of no significance. So they don't even bother to use a defined variable here. Basics got fancier. So in this 8K basic, the OSI one, random of x with the same x always generates the same sequence of numbers. Random of 0 generates the same number always. So it's not even a random in this one. And this one, if you call random of 1, random of 1, random of 1, you'll get 3 different numbers, most likely. But if you call random of 2, well, you'll get a different, you'll get numbers from a different sequence. Let's just do the original way for now. Okay, so if you say rand, well, we got to get value.function of function n to n. Well, the function is, we're going to ignore the argument n, and then we want to find Swift's random number generator. Okay, so generate random float. Right. We don't really want to do that. They've been increasing it. Okay, extension int.random. Okay, let's go find documentation. Swift float. I'm hoping there's just a float.random. So we're not going to worry about, in a range. I really want, let's see what range of float does. Okay, I guess I want that. 0 to 0 less than 1.0. Okay, so we'll use float.random in 0.0 up to 1, because the random number generator they use, the typical one, it's closed on the 0 side, meaning you could generate a 0, and it's open on the 1 side, so you will never generate a 1. Okay, but anyway, this thing is float.random in 0.0 ... less than 1.0 in bracket print. Okay. I guess I did. Isn't that funny? 0.0 ... accepted separator. Maybe I need spaces around there? Dot less is its own thing. Didn't we just see an example? In dot less. Yeah. Let me build. Expected separator. Fix. Oh, that separator. Okay. Random. Okay, what else we got? Signum. Tab, we're not going to do. User, we're not going to do. EXP, we can do. And log. And then, oh, there was something else in here. Somewhere it tells you that square root and log are done on their absolute value. Okay. Random. Signum. Okay, good old SGN. SGN. Okay. Well, this one. $0 equals 0, then 0.0, else I don't know. Is that too clever? Let's space it so you can at least read it. If $0 is 0, then it's 0. If it's less than 0, it's -1. Otherwise, it's 1. That's about the worst ternary I would ever want to write. And let's see, does Swift have a signum function? It does. Okay, good. Well, let's see if it's on float. Or double. Hmm. Let's do this the other way. If $0 equals 0, return 0. Else, if $0 less than 0, return minus 1.0. Otherwise, return 1.0. That ternary was just too much for me. Okay. And based on not seeing a signum function for double. Minus is not the same as less than 0. Okay. Yeah. Okay. I don't think it exists. All right. Sine, cosine we did. Square root we did. Tab user not worrying about. EXP freeze not worth worrying about for us. EXP and log. All right. I'm just going to put them in, and then at some point we'll write a giant test that calls them all or something like that. And I think it's probably called EXP, yeah. And log. Pause and space. Again, they're really more print things. Okay. Let's make sure tests run, recognizing that we. And I think I'll make this say test predefined numeric functions. Haha. Okay. Interpreter. User defined function must. Wait. Does that look right? Oh, we get some different output. Right. This is no longer an interpreter test because we enforce this in the parse time. So there never can be a problem like that. But let's find this text. Okay, the test goes away. The text, on the other hand, right. Function if expert type not equal operands type sub 0. All right, so we no longer need to test this here because we've already done our type check on the operands. Okay, so changing my argument from yesterday. Same thing here. We don't really need to check the operand types because we've done that. All right. Now, do we do these? Internal error. Okay, this, we don't need the type. This is the function lookup, so we don't care what the type is. We're just verifying that it's there. Right. Okay, let's see if this is better. Okay, so that means I didn't run tests at some point. Add most of the numeric predefined functions. Remove runtime type checks since they're enforced at parse time. All right. Handle the case of a missing predefined function. I don't think we're gonna. That's not our. Theoretically, it can't happen if we've defined the same functions across the board. Test predefined numeric functions. All right, I'm gonna defer some of this stuff. Again, I don't know. Is it boredom? Whatever. It's partly it's that I feel like these problems, it's kind of a question of which problems are interesting to me, I guess. I'm not worried that, I mean, I know I can go fill in these string functions. I probably have to write little helper functions, but they're not hard. They're not very interesting. The expression parser from parser, that's a little more interesting to me because I feel like the parser is just becoming really, okay, it's almost 500 lines. I'm not sure it's better if it's 250, but the expression piece is a huge piece of this thing, and I'd like to improve it. Yeah, it actually is just about half, isn't it? Okay, here's expression. And probably some of these helpers are really associated with that. Maybe it's just not enough to be interesting. I don't know. But I would love to to simplify the parser a bit. And I don't know. The other one that bubbles through my head is I've done this recursive descent approach. There's another way to do it where you it's still top-down parsing, but you put the rules in a table and do them that way, so that you have basically a grammar table, and then you define some routines that get run at the end of each grammar rule. So I don't know. I don't know if splitting it's going to help that much, because it seems like a lot of what's there is just kind of what's needed for these expressions. A thing that could be done, I don't know if it's a good idea or not. A lot of these things have this structure. Left equals try the next lower level down, and then while we look for a matching token out of a list of acceptable tokens, or just has or at that level, but plus and minus are at the same level. You could have a generic function that takes the next level down. The list of acceptable functions, I don't know. I don't know. Is that really better? But there is some similarity here, right? This, it's calling the next level down. It looks for a matching token. It does a while loop, checks the float types, and it just It's very mechanically the same. This one is different because we got unary minus and relational. We have multiple tokens that are acceptable, but it's still try expression, consume the token, try a sub expression, require some sort of semantics. It's very similar, and this one's very similar. All the way down, one for each precedence level. Now, another thing I could do is there are approaches where you basically define operators, like define their precedence level and whether they're left or right associative, and then how unary fits in. That's doable. That would fold this down into kind of like one routine, slightly more complicated. And we did that. I don't know, my Twitch sessions probably last year, maybe the year before even, of parsers, a few types of parsers. And we had one of the ones that did the precedence parsing kind of thing. It's not bad. I mean, the problem with precedence parsing, what I recall is that you can, you define these tables, and if you have places, how do I say it? Basically, I think a precedence parser can miss syntax errors because it just sort of assumes, like, you wouldn't give me two operators in a row. Of course you wouldn't. So you still need something to kind of enforce those rules on the outside, even though it would just, happily shove things on the stack and compare them and all that stuff. Yeah, so that kind of bugs me. But then you get down to the bottom level, and you're just going to have to do this factor. It just has a bunch of cases. Ugh. Yeah. Okay. Now, I wonder if the user-defined function and the predefined function, can we make those more similar and call a single thing? Function require, this part's the same. Friend operand types. Left parent expression require type check. Operand types would be this, and expression is still just one. Maybe you could. We don't start the same, but we end the same. Okay. I'm gonna kill this one. I don't think we're gonna do that. Error handling in the interpreter. Well, this is another one that it's a moderate sized change. I don't even know if I could call it a refactoring, because I'm gonna switch it from returning some weird strings to throwing exceptions, basically, is what I'm anticipating doing here. But I think we probably should do that. This sort of thing, it really should be a throws. I don't know, we got question marks, internal error. Well, really, that's the only one. Well, maybe that's not worth it. This is the undefined user function, huh? don't know. We don't have a lot of cases where there are errors. Oh, well, here's an undefined. I guess divide, right? You could divide by 0. Okay, I'm not so convinced we need to do anything here then. I thought this was much more pervasive. I don't think I care what the messages are, so let me make them all put question marks on there. Okay. Yeah, I'm pretty sure I don't check those. So let's look for quotes. Okay. All right. The other one in my head was the Lexer. Now, we split out these one character situations and the reserved words. The other one, okay, so we got these, we got numbers. There's still something going on with line numbers. I don't think we're doing, I don't know. I feel like the way we handle integer for line numbers is still goofy. So what we have a challenge for is like normally the only integers, true integers, are line numbers, and they have to be in the range 1 to 99999. We don't enforce that, I don't think. But if you see an expression like print 3 plus 2, 3 and 2 are supposed to be floating point numbers, and yet they look like integers. So our parser just says, well, I really expect a line number at the beginning of the line. If you're not there, then I assume you're going to be an integer of some sort. I mean, a float. That's, I don't know, that's still not quite the right thing. I think what we need to do, because there are, well, you can say go to some line number. Well, now we have to know that if you see the word go to, the next thing might be a line number. Let's see who sets this. Okay, so we're in a then. Okay, if x equals 0, then 20. Oh, we're looking for a line number. But the more modern basics, as of 1982 or whatever, but the 1980s basics, they allow you to do things like if x equals 0, then print 3. And now you're not looking for a line number, you're looking for you're looking for an expression again. So I think we're going to have to visit this again. This is handling integer line number versus float. Okay, let's see. We did this. To what small extent we're doing it. Okay. I think we're going to have to resolve that. And I think this looking for line number thing, it's a hack in the lexer that it has to kind of maintain this state to know this stuff. I think instead we'll just say you can return integers or you can return floating point numbers based on what you see, and then in the expressions, when we see a factor that's an integer, we'll convert it to a floating point number right then and there, and nobody on the interpreter side will be the wiser about how it started life. Okay, I'm liking that one. Okay. Do we want to do that now? All right, let's make sure I haven't changed anything. Okay. All right. Yeah. So what was the other thing in the lexer? Let's see. Where's that big switch statement? Okay. If it's less than, it can be less than operators. Equals okay, but less than operators, I don't know. It's a very specific thing. Like if it finds a less than, then it looks at the next character for an equals, and then if it wasn't an equals, maybe it's a greater than, which means not equals. Otherwise, it was just a plain old less than. I think we could do something very much like we did for the A to Z stuff, and just say if you see some string of less thans, equals, and greater thans, run through this list of possible things, just like the single operators. We could have multi-char operators that would be string to token, and they would work a lot like reserved words, where we look at the prefix of the rest of our input and say, does it match one of these things? I don't know. We're talking about 8 lines difference, and I don't think that's too bad. Okay. Yeah, down in here, we have to keep track of whether there was an exponent or a decimal point. And if we had 45 E3, that's still a floating point number. Yeah, but we did the code for that earlier, but okay, here's integer. And we can call integer because we know we're looking for this particular case of integers. All right, let's do this one. And yeah, the reason for this, let's find. Yeah, we have goto, which could be needs an integer line number. Go sub, which takes an integer line number, and then we have these ons. Well, if goto, I guess this basic doesn't do print or anything. You can only do goto or then. All right, but on goto takes a list of line numbers after the goto. Yeah, so even then is not enough if you Oh, they allowed instead of then. Okay. Yeah. And I don't know, maybe that we've gone a lot of time on these functions and expressions, and we still haven't done subscripts. It's such a huge piece of the language. I mean, it looks subtle here, just like, oh, there's an expression, but there's a ton of stuff in there for that. Most of these other constructs aren't too bad. Um, we got more to do on print. The data read and restore, they're pretty easy. Um, yeah. Oh, there's another integer, dim a. How many? I don't think it matters that it's an integer. If it were a float, if you said 12.0, it would still convert to an int and do it. That's probably fine. And I guess this integer thing is one of these back and forth decisions, but I think the place that I think these places like this that know they want an integer will be happier if it is an integer. The places where it's ambiguous is in expressions, and we can deal with it. So, all right, let's go with this again. All right. I guess we're due for a break. Let's take a quick break, 2 minutes, something like that, maybe 3. All right, see you in a couple. Welcome back. All right, so we will start with our Lexer tests and just go through and see everywhere that makes assumptions about integer or float. All right, so these line number ones, they have to be integers. We should check for the size range. Let's add something for that. Check line number range 1 to 99999. Okay. Lexer tests. All right, integer numbers past line number expect float. Okay, I think this one's the first one. We're going to say this should be integer 20. May still be integers. Okay. This test should fail. What? What was... Wait a minute. It said... Okay, let's make sure this test passes before we change it. Okay, now I'm saying this test should give integer 20. I don't think it's running my test when I say it should sometimes. Yeah, okay. Numbers past none number may still be integers. May still be integers. Okay. Remark. All right. So this one, I think we're all right. So var is float equals false. Let's start there. I think that's actually really our initial state. Okay. If we see a dot, is float equals true. And if we see an E, then is float is true. I might move that down a line. Okay. Just because we always want to make sure we get through incrementing index. Okay. Now here, if it's is float, then token number, else token dot integer of value. Okay. Let's see how this test does now. Okay, so I think looking for line number, then if I take this out and just return number, we'll just comment it for a moment. Okay. This test should be fine. And I don't know who calls this. Nobody. No. Is not being used otherwise. Okay. All right. Now we may have other places that relied on this. So let's run all Lexer tests. Okay. And I'm still expecting at least one or more. Okay, good. First token always expects an integer. Well, okay, where's the Lexer test? First token always expects an integer. That seems like it should be true. What is it coming back with? Exponent value is missing. Oh yeah, that's right. We ran across this error. Let's see what else we got. Print a number. Integer for this can be integer 42. Okay, that's fine. This should be integer. Okay. All right. Digit gets number. Well, okay. Again, now we should be down to one failing test. This one end thing. Okay, if program subindex is E, well, if it's E, then we know index plus 1 is still valid because we always have a new line. We also know end is the only word that starts with a number. So if program index is E, okay, we know this case doesn't happen because we've upcased everything. We've standardized it. Okay, if program, I guess if program subindex is not equal n, this is a weird case where we're looking ahead 2 characters. And I believe end is the only reserved word that starts with E, right? So, I hate to. Okay. This context. If it starts with E, the next character is not N, then it really is probably an exponent. I could get pickier. Would it help to say less than A? I don't know. Do we have a... I don't know if I can test a range. If the next letter is an E, but the following letter is not a numeric, an alphabetic letter, then it could be an E plus E0. I'm probably saying this backwards. I think I can do range.contains, something like that. Yeah. It's a little awkward. Okay, if we see an E and the following letter is not an alphabetic letter, then it is a true exponent. And we should say is float true. Okay, so let's see if that works. Oh, do I still have 2? No, this one's saying it failed. Let's see. Okay. results. Okay, good. Now, I expect a bunch of parse failures, or at least some. Okay, that's a bunch. 75 of them. Okay, print 42. Okay, nothing. Yeah, so these are pure integers. They didn't get converted to float. So let's go in our parser. All right, and our factor. Okay, left paren, right paren, number. Okay, let's deal with integer. Else if case integer, let int value equals token. Let's see, numeric factor. Okay, I think we can use that same one. We're just going to convert it to a float first. All right, this should take care of a number of them. Maybe all, but at least, yeah, bunch. Okay. Multi-line program and fall off the end. $30, $50. Okay, 25, go to 50. Well, that's interesting. Okay, that's an interpreter test. Let's go back to the parser level. Go to, okay. Missing target. That should be fine. Missing target. Let's go to. The parser handling go to. Okay. If case number, well, we actually want integer here. Okay, so if integers are always parsed as integers, okay, then we'll always get integer for this token if it's properly formatted. We don't want to say go to 37.5. So let's do that and run them all. I noticed the interpreter test that failed was a go to test, so that's probably a good sign. All right. I think that's acceptable, and it solved some problems in the Lexer. This is like the unfortunate piece of that, but it's kind of somehow we have to deal with it. Okay. Let's see that float. I've got a comment here. I think that variable, yeah, looking for a line number, that should go away. Somewhere we commented something out about it. There we go. Okay. Let's build. Okay, so we were saying If a then is followed by a digit, then looking for line number is true. We don't need this case anymore. We always look for a line number integer now. Okay. So that should delete. Alrighty. To do like integer line number versus float. Okay, makes Lexer always look for integer where possible. Adjust it on float to factor, but leave it integer so line number references get integers. Not my best comment, but we'll get through it. All right. Check line number range. Let's see. So this is parser. We do single line, calls line. It checks that we have an integer. Well, this is always an integer now. We don't need to call it a... Oh, is that an integer? Is that true? It is an int. Okay, so that was kind of a can't happen situation. Case integer, let's call it int value. Okay. Well, I think we can just say let line number. Line number equals int value. Okay. Okay, so we check the case of no line number. Okay. And then we parse return line. Okay, let's make sure this is good. Good. All right, and let's make a test for this. Just an int and rem. Okay. Mostly we're getting the line number. Yeah, let's do an error test. All right, test 0 and is error. Line number range, I'm making that up. Okay, no line number range. This should fail. Okay, and I think let's go ahead and add the other end. 100,000. Okay, it said 5 digits, so one with 6 is too much. Both these should fail. Okay. And single line integer. Okay. Do you say const? No. Okay. Oh, I said less than 0. Let's call this test line number range. Number is in range 0. Let's check line 1 and see, that didn't run. That's worrying to me. Okay, 127. So, check line number. Okay, slowly getting more errors. Okay, do. Okay. Statements, I don't know. Okay. Somewhere I feel like I should list out the rest. We've got more statements to do, so let's get those listed. One cluster is the data statements. Data, read, I think it's restore. Dim, we got to do subscripts, so we got to do dim statements up here. Dim. We do end. We don't do for next. That's a good one. Go to, go subreturn. I'm not going to worry about if go to. I think we can handle that more generally. On goto though, and there's on go sub. Well, I guess that was a more general thing. Print, read, rem, restore, and stop. Stop's pretty easy. It's like end mostly. Okay. Test predefined numeric functions. Ew. I think we want to get what was free. Let me just make this one return a constant. Free. Interpreter. What do we have changed? Nothing. Okay. Interpreter. Value function. The function is ignore the argument in, and let's just say free space count, and we'll make that a float. I think I can do these, right? Can I convert value of type int to closure result type float? Replace free. I guess. No. Okay, far more than any of these old computers would have. Right. Okay. Let's see. I think I want to stop there. Next time we'll I don't know, maybe we'll do I think we'll just have to bite the bullet and finish these finished functions, expressions with numeric or string functions. Once that's done, I'll feel better. Yeah, hopefully that's our last day on functions for a while, and then we move on to subscripts, and with that we'll finish expressions completely with subscripts in the dim statement. Then, yeah, I think that'll do us. Okay. Print is moderately complicated. I'll probably want to do some of these other ones in front of that. Multiple statements on a line. You know, I brought up that amazing maze, and I think I'd like to get, like, what do we do to get that working? I know it needs this, so I'm going to move this one up a bit. And I know it needs multiple statements on a line, and I think it needs this one too. And it certainly needs for next. And it certainly needs go sub. Okay. I know it uses subscripts, so I'd like to be able to run that maze. That would be a very good point to get to. And then we can worry about the complexities of print and so on. I do have some stuff that's kind of compiler type stuff. Like we don't tell you what line number your error is on. We just tell you like, there's an error. You made this parse error of some sort. We really should print the line number and really, I would feel better the column number. Syntax errors. Okay. And, something can display that and make that go. Yeah, I think that would be a step forward. Skipped forward to next line number. Yeah, that would be good too. Okay, so we will stop here. The next time is tomorrow morning, 10 a.m. to 12:30 Eastern Daylight Time, and 3 to 5:30 p.m. UTC, and otherwise I'll let you adjust it to your time zone. Thanks for joining. I hope you have a good evening, good day, and I'll catch you again in the future. Bye-bye.